Hey guys, today we're going to talk about different types of distributions. So, first of all, we talked in the past about histograms in the first lesson of the unit, I believe it was, and we talked about how they make these different shapes, all right? So these are all of the shapes that they kind of make, and we're going to talk about what kind of things these tell us, okay? Whoops. Okay. So, So the first of all, there's two sort of categories here. They can either be symmetrical or skewed, all right? So the three primary symmetrical ones are the ones you see the most often, are normal, bimodal, and uniform. And then the skewed ones, which just means that they're not symmetrical, you can have right skewed, left skewed, and exponential, all right? So the most important one we're going to talk about, and the one we're going to talk about quite a bit here, is normal distributions. And this is kind of your standard distribution that you see all over the place, and we often call it the bell curve, okay? So the normal curve, or normal frequency distribution, is a hypothetical distribution of scores that is widely used in statistical analysis. So what's important here is it is hypothetical, and what I mean by that is when you have a histogram, it's never going to be a perfect smooth line because, of course, it's made up of little bars, so it's going to be quite jagged. And so the idea is that we look at it and we make the assumption that it is a bell curve or a normal curve, and thus we can do a bunch of statistical analysis with it. And there is some estimating in it. There is some, approximation just because it is just a hypothetical distribution, okay? It would be impossible to actually get this exactly. Okay, so since many psychological and physical measurements are normally distributed, the concept of the normal curve can be used with many scores. Okay, they're fairly straightforward. And the characteristics of the normal curve make it incredibly useful in education and physical and social sciences. Okay? And so, as I say, education, that's the one, when you go to university, and you get your test back and it says that you got a 60%, you can be excited when the prof then tells you he's going to bell the marks, because that 60 could turn into a much, much higher mark because it means everybody bombed the test. So anyway, that's a process we're going to talk about a little later. Okay, so characteristics of normal distribution. So the normal distribution is completely symmetrical around the mean. So this point here, this middle point there, is the mean, okay? The distribution is often referred to as bell curve. We already said that. Okay. Let's see. I can't turn pages. Oh, come on. There we go. All right. Okay, the curve approaches the x-axis in both directions but never touches the axis. So that's worth mentioning. So if we look at the ends here, this x-axis in both directions is an asymptote. It never actually reaches that. And that's because theoretically you could go for forever in each direction. Okay, the one example of a normal distribution that I often like to refer to, just because it works really well, is an IQ score. IQ scores are a normal distribution, and the idea here is that even though most people are centered around 100, you could theoretically have as high an IQ as possible. You could just keep going. You could have 6,000 IQ. It's so incredibly unlikely, but theoretically it is possible. Okay. Let's see. So the total area under the curve is 1 or 100%, and that makes sense because that would be the sum of all of the probabilities together. Okay. So let's see. Okay, so normal distribution can be completely described by its mu, its mean, and its standard deviation, the sigma. Okay. So when we talk about a standard a standard distribution, we will just give the information. You'll be given mu and you'll be given sigma, and that's it. You'll actually be given sigma squared, but that's irrelevant. We'll get to that later. But that is enough to completely describe the data. All right? Almost all the data lies within 3 standard deviations of the mean, and indeed you can see I've got this picture here. So there's your mean. If we go out in 1 standard deviation from that mean, okay, within that interval, so let's say your mean was 5 and your standard deviation was 2, then between 3 and 7 would include 68% of all of the data, okay, within that. Okay, if you go out another one, you now are including 95% of all the data, and if you go out the third, you have 99.7% of the data, all right? Okay, so that's, and so this is how we write that then, is we'll often write that as mu minus sigma, mu plus sigma, so sometimes we'll write mu plus or minus sigma, depending what we're doing, okay? And then you just multiply the sigma, okay, plus or minus 2 sigma, mu plus or minus 3 sigma, okay? So that can describe those intervals very well. So the way you're given it, so what's written when you're told it's a standard or it's a normal distribution is you'll be given something that looks like this. And what this means is the x represents the data. So the data lies in, or is modeled by, and then the capital N means that it is a normal distribution with a mean of mu and a variance of sigma squared, which we're about to talk about, I think, but variance, oh, maybe that's not till next lesson, it doesn't matter. The point is that sigma is the standard deviation. So it actually gives the standard deviation squared. Now it is worth mentioning that almost never, so when I said, I described the one example, I said, what if we had one that had a mean, whoops, I forgot my n. Well, let's try this again. Okay, so I would say it's a normal distribution. It has a mean of 5, and it has a standard deviation of 2. You wouldn't write 2, but you also wouldn't write 4. You'd actually write the 2 squared. Okay, and is that stupid? Yes, it is. Do I know why they do it that way? No, I do not. But that's what they do, and so whatever. Get used to it. Okay. The standard normal distribution is given by this, okay? So the standard normal distribution, so the key word here is this is the standard normal distribution, okay? They're all normal distributions, but if you have the standard normal distribution, what's important is that you have a mean of 0 and a standard deviation of 1. That makes it the standard normal distribution, all right? And that's something that we'll get into when we talk about z-scores, which I believe is your next lesson. We'll talk about how we can force data to fit the standard normal distribution, and then that way we can directly compare different data sets. Okay. So an example here, we got a pair of dice were rolled 75 times. After each roll, the sum was recorded and graphed. So there it is. And we've got this note here that points out that even though this is not perfect, it's not completely symmetrical. Okay, if you look, 7 goes up a little higher than the 5, okay? But it still has that bell shape. And the idea is that in theory, if you were to roll those dice an infinite number of times. Now, I should point out, this should be a histogram, and it's not. The bars are not touching. Those bars should be touching. They should always be touching when you're doing a histogram. So we'll just forgive that because I copied that off of something probably. Anyway, so it's not perfectly symmetrical. It's not perfect, but it's a theoretical model, and so it does fit the definition of a normal distribution. Okay? All right. So that's it for that. We'll get a lot more into the normal distribution when we talk about z-scores in the next lesson. Okay? All right, so let's talk about bimodal distributions. A bimodal distribution, you can see I got a little picture here. It kind of looks like a normal distribution, except that it's like 2 of them. Okay? So there's the peaks, and we're assuming the peaks are of equal height, so then it has 2 modes. Okay? So each of those numbers would be the mode in that case. Okay? Intervals with the highest frequencies are either end of the graph. Okay, so it doesn't have to look exactly like that. Like it can be, like as long as you see 2 peaks, that means that it has this bimodal. Okay, that's what's important there. And then it has a low point in the middle. All right. The mean and median are not necessarily equal and are located between the 2 peaks. So the mean and the median would be somewhere in there. Okay. They might be the same, they might not be the same, all right? In the normal distribution, they were both the same, okay? And a bimodal distribution often indicates there are two subgroups to the data which should be examined independently. And that's the thing about a bimodal graph, is it's actually incredibly interesting when you get one, because it does just mean somehow you've got two groups, two separate pieces of data sets somehow combined into one. And so when you're doing your final project for your culminating this year, you could maybe get data that when you graph it, it looks like this, and that just means that there's so much more you can do with it, because you've got to figure out, how can I separate this data into two separate groups and look at these independently? Okay, so an example here is if we've got a class of grade 6 and grade 1 students, and we measure each of their heights and record and graph them. Again, we get a bar graph instead of a histogram, but the idea here is you've got two peaks here, okay? This is obviously the kindergarten kids. This is obviously the grade 6 kids. So we actually have two sets of data. Now, it's not like you could have, it's possible that we've got one person right there that is a kindergarten kid. It's unlikely, but it's possible. We could have one kid right here that is from that grade 6. But the majority of the data for the grade 6s is like that. And then the majority of the data for the kindergarten kids is like that. So I've actually just combined two data sets essentially. Okay? So that's a bimodal distribution. Okay? Uniform distribution is the boring one. Uniform distribution means that it's pretty much just a straight line. Okay? It's not exactly straight. If you look at this one, there is some variation. Okay? But in theory, if we went for an infinite number of times, it would all even out. And that's uniform distribution. So the example here, rolling a die 50 times and recording it, you have equally likelihood for each outcome. And so over time, it's just going to balance out. Okay? Skewed distributions. Skewed distributions are pretty straightforward. It kind of has a similar shape to the normal distribution, except that it's lopsided. So you can see that this one goes up faster and then slowly trickles down. And you can see the mode is going to be right at that peak, okay, because that's what a peak is in a histogram. The median comes next, and then the mean comes finally, or is the last one there. And that's because, of course, those outliers, remember, have that huge pull on the mean. They really dramatically affect the mean, even though they don't affect the median as well. Okay, the one mistake that people very commonly make on these, this is a right skewed graph because the tail is on the right. People often look at this and think it's left skewed because of more of the data is on the left. But the skew is the tail, okay? So this one is left because that's on the left. All right? Yeah, and the left skewed one is exactly the same as the right skewed. It's just the mirror image, okay? All right. Oops. Well, I'm back to not being able to turn the page. I can't figure this thing out. There we go. All right. Okay, so here's an example. Sally picks up a handful of quarters and records the year on each. Obviously, she's going to have way less of those really early ones. She's going to kind of hit a peak, but then there's probably not very many of the brand new ones. So it's going to have that skewed. This is a left skewed because the tail is on the left. Okay. Okay. Exponential distribution. So this one is, there's not very much to say about this one, to be honest. Okay, this is just it starts at the top and then slowly goes down. It's not quite like it's not quite the same as a skewed because the skewed goes up and then goes down. So that's skewed. Okay, this one, it just starts at the top and goes down. Now, it is possible for an exponential one to go the other way, where it goes up like that and goes on forever. It's not very often that comes up because it would actually have to go off forever. So that's not something you're typically going to see. Okay, what did I just do? Oh, whew! Thought I erased everything. I meant to do this. So we're not really going to talk about that, and that's not something you'll really see. Okay, what's important is this one, where you start at a very high likelihood and then it just drops off. Okay, and I believe that's it. Yeah, that's it. So until next time, go Sabres.